and this lesson is entitled Reducibility of Polynomials. When we started learning polynomials, we learned how to add, subtract, multiply, and divide polynomials. And as a comment, we have learned that multiplying polynomials is a hard problem computationally because we are repeating the application of distributive property a large number of times. This happens especially when the degree of the polynomials involved are big integers. If polynomial multiplication is hard, then factoring a polynomial can, can be very hard as well. In fact, it is even harder because there is no definite step-by-step procedure on how to factor polynomials, especially when the degree is large. So in this lesson, we will be asking the following question. When can we say that a polynomial is factored completely? And if a polynomial can be factored, how can we know in advance? Are there tests to know whether a polynomial can be factored? In abstract algebra, we set up a setting where this can be discussed rigorously. Polynomials which can be factored are called reducible polynomials in abstract algebra. And polynomials which can't be factored are called irreducible polynomials. Now, what do we mean when we say that a polynomial is factored? By this, we actually mean a non-trivial factorization. For example, let's go back to the ring of integers. We know that in the ring of integers, the only units or the only elements which have multiplicative inverse are the elements 1 and -1. We have learned from elementary arithmetic that every integer greater than 1 can be factored into prime factors. Now, these prime numbers are also known as the indivisible integers because they can no longer be factored, or if they can be factored, they can only be factored in a trivial way. Now, what do we mean by a trivial factorization? For example, if you have a prime number 7, let's write down here, 7 is prime, right? The only way to factor 7, disregarding the order, is 7 times 1. As you can see here, this is a trivial factorization because 1 is a unit. Or I could even factor this if we consider the negative integers as -7 times -1. This is why an integer n greater than 1 is prime if and only if, whenever we factor p as a times b, one of the factors a and or b is plus or minus 1. In other words, one of the factors must be a unit. Also, let's recall that if d is an integral domain, then the units of the polynomial rings, or the only polynomials with multiplicative inverses in this word bracket x, are also precisely the units of the integral domain D. Now, the units that I'm talking about here are the polynomials or the elements of D when we view them as constant polynomials. So, we make a definition parallel to these ideas. So here, we get an integral domain D and a polynomial p of x over D, which is non-zero and non-unit. Okay, first of all, we do not consider non-zero and the zero polynomial and the unit elements in this case. We say that p of x is irreducible. So we are first defining what we mean by irreducible over D. So we also talk about the set involved. If whenever we can factor p of x as a of x times b of x, then one of these factors will be a unit. In other words, a polynomial is irreducible if and only if it only has or it only admits a trivial factorization. Again, when we say that the factorization is trivial, it means to say that one of the factors is a unit. If this is not true, if it is possible to factor p of x into non-unit polynomials a of x times b of x, then we say that p of x is reducible over b. So for the rest of our lecture, this is our definition. We just have one more remark before we continue. Recall that a field is an integral domain. So sometimes the ring of coefficients can be a field. In the case where f is a field, we know that the units of f square bracket x are also the units of f. But the units of f, because f is a field, are precisely the non-zero elements in f when viewed as constant polynomials. Thus, we can say that if p of x is reducible, then we can express p of x as the product a of x times b of x, where, what can you say about this? This should be non-unit. Can you say that these are polynomials which are not constant, right? So the minimum degree of a of x and b of x should be 1. Therefore, in over a field, a polynomial can be considered reducible if it can factor it into two polynomials which are non-constant, right? Non-constant, so the degrees are greater than 0, but at the same time, their degrees is less than the degree of p of x. Why is that so? Why do we require that? Because if one of these has a degree same as the degree of p of x, recall that we have learned that over an integral domain, the degree of p of x is the degree of a of x plus the degree of b of x, which is a property, right? So if, let's say, the degree of a of x is equal to the degree of b of x, this will force the degree of b of x to be 0, and that will not be allowed because we don't want unit factors, right? So again, when we say that over a field, we say that a polynomial is reducible if we can find non-constant polynomials as factors, meaning to say the degree is at least 1 or linear, so that the product of these polynomials is the given polynomial, and these polynomials have smaller degree than the given one. So let's consider this example. Well, we know that Q is a field. Is x squared minus 2 reducible over Q? Well, the answer is no, based on our experience. We have learned that x squared minus 2 cannot be factored into two polynomials of lower degrees, none of which is constant, no? Right? So that their product is x, so that their coefficients are rational numbers, and their product is x squared minus 2. Well, to prove this claim, no, how can we prove that it is not possible? First of all, notice that the degree of x squared minus 2 is 2. So the only possible non-trivial factorization is when the degree of the factors are both 1 or they are both linear. So for the sake of contradiction, suppose that x squared minus 2 can be factored as a product of two linear factors, let's say ax plus b times cx plus d, right? Where a, b, c, and d are rational numbers. Okay, now simplifying the right hand side, if we multiply the right hand side, we get ac x squared, so I will not be showing you the details anymore. Just want you to verify, plus bd. Now two polynomials are equal if their corresponding coefficients are equal. So this will give us the following equation. AC equals 1. Looking at the terms x squared, looking at the terms x, we have learned that AB plus BC is 0. last but not the least, BD is equal to negative 2. Alright, so what we do here is we look at the consequences of this equation. For example, if we look at the equation 1 implies that actually C is 1 over A. Remember that uh, A, B, C, and D are rational numbers. Now here, by the way, A is not 0 and C is not 0, otherwise these factors will be constant. So we don't want that over a field, right? Okay, so C is 1 over A from equation 1. Now we will plug this into equation 2. We will yield AB plus B times 1 over A, that's B over A equals 0. So simplifying this, get A squared D plus B all over A equals 0. But this simply means A squared D plus B is equal to 0. Now to be able to use equation 3, what I'm going to do is I'm going to multiply both sides of these equations by D. So I get A squared D squared plus BD equals 0. But what is BD? From equation 3, BD is negative 2, so I get A squared D squared minus 2 equals 0. Therefore, AD squared equals 2, and AD is a rational number. Now we have learned that there is no rational number whose square is 2. There are lots of proof, right, out there. So therefore, this is a contradiction. Hence, we could not factor x squared minus 2 as a product of two linear factors. Therefore, it's irreducible. So therefore, x squared minus 2 is irreducible over 2. That's the answer. Next, how about, is x squared minus 2 reducible over r? Kanina, ang sagot natin, no, over q. But how about over r? Is this reducible over r? Can we factor it into real polynomials of degree 1? Actually, yes, right? No? We could express this as x minus the square root of 2 times x plus the square root of 2. So, the idea, well, the question whether a polynomial is factorable or not, or reducible or not, it depends on the domain that we are talking about. You see that over the rational numbers, x squared minus 2 is irreducible. However, over R, it's reducible. It will follow that because C, the field of complex number, is a field larger than R, if the polynomials over R can be considered as polynomials over C. Therefore, whenever you are reducible over R, you are automatically reducible over C. When you look at the polynomial x squared plus 2, now, we can do a similar computation, just like in this example, right? You can just repeat the process. You will find that this one is irreducible over R. In fact, by our experience in algebra tells us that this cannot be factored into real linear polynomials. However, this polynomial is reducible over C because I could express this on, wait, burahin ko yung parenthesis. I could express this as x plus square root of 2i, x minus the square root of 2i. Meaning to say, I need complex numbers to be able to factor this. Okay? Over Z. Right. This time, Z is not a field. So, uh, remember the reducibility condition for a field may not hold for Z because Z is not a field. Question is 2 times x squared plus 4 reducible over Z? Notice that I could express 2x squared plus 4 as 2 times x squared plus 4. Now over Z, this is not a unit, What are the units, by the way, of z squared bracket x? The units of z, which are plus or minus 1. So this one is not a unit. 2 over z is not a unit. It doesn't have a multiplicative inverse. So this is also not a unit. So therefore, over z, the polynomial 2x squared plus 4 is reducible. How about over q? Can we factor this over the rationals, no, in a non-trivial way? Well, you see that the only way to factor this over q is like 2 times x squared plus 4. But this time, because we're talking about q, the element 2 is now a unit. 2 has a multiplicative inverse now, which is 1/2. So therefore, this is just a trivial factorization, unlike when you do it over z. Okay? So this is not this is not what we want when we say v factor over q. Okay? So actually, this is irreducible over q. No. Pero over z, it is reducible. Well, this polynomial is famous, the polynomial x squared plus 1. This leads us to the invention of the symbol I, remember? So we know that x squared plus 1 is irreducible over r. It's being used a lot of times in basic algebra. But notice that over z sub 2, when we view this polynomial as a polynomial over z sub 2, using the freshman's dream theorem, we know that over 2 or modulo 2, x squared plus 1 is the same as x plus 1 quantity squared. The reason being is when you expand this square using the binomial theorem, the middle term 2x will be zeroed out because we're doing it modulo 2. Hence, x squared plus 1 will be factored into x plus 1 times x plus 1. Or we should just write x plus 1 quantity squared. Hence, x squared plus 1, although it's not reducible over r, it's reducible over z sub 2. So sometimes reducibility generally depends on the field or on the ring we are talking about. So, as you may have noticed, determining whether a polynomial is reducible or not is a hard problem. Of course, the next question is how can we make it easier? So first we have a theorem, but this theorem covers only those ring of polynomials where the ring of coefficients are fields. So here, f is a field, p of x is a polynomial whose degree is at most 3. So, only quadratic or cubic. So, hindi na ito covered yung mga polynomials of degree 4 and up. Then, p of x is going to be reducible over f if and only if. So, this is a necessary and sufficient condition for reducibility. But only, take note, when the degree is either 2 or 3. So, the condition is that whenever p of x has a root in f, then p of x is reducible. Well, this is almost obvious, but because if p of x has a root in f, then let's say r, then x minus r is a factor of p of x. Therefore, it can be reduced. That's the idea, the general idea. But for the formal proof, let's do the proof of sufficiency. Is this a proof? Yeah. Okay. So assume that p of x is reducible over f. So this is I forgot to write here over f. Just insert it here. Then, by the definition or by the remark, because f is a field, then we can express p of x as a product of two polynomials, the degree of whose are greater than 0 but less than the degree of p of x. Right? Because of this equation over integral domains, this degree formula or degree formula works. The degree of the product is the sum of the degrees of the factor. Works if the ring of coefficients is an integral domain. And because this is of degree 2, there is only, well, two ways, or actually one way. There is basically one way to split um, fit the degree of p of x, then it must follow that one of these must be 1. Now, for example, if this is 3, then the only way to split that is 2 plus 1. But if this is 2, the only way to split that is 1 plus 1. Bawal ang 0, right? Right. So, 1 of u of x or v of x is a linear polynomial or degree 1. Let us just say without loss of generality that u of x is the one that is linear. So you can express u of x in the form ax plus b, where a and b are in f because u of x is linear, a cannot be 0. Then we know that this linear polynomial has a root. In other words, this solves or this makes this equal to 0. Therefore, this serves as a root of u of x, and because u of x is one of the factors for p of x, and because f squared bracket x is an integral domain, it follows that this is also a root for p of x. Therefore, we have shown that if p of x is reducible, then p of x has a root in f. So we're now going to prove the converse. So here we assume that p of x has a root. Let's say the root is a, we know from factor theorem that if a is the root of p of x, then x minus a is a factor of p of x. Therefore, finish. Because if x minus a is a factor of p of x, then the other factor has to be at least linear, right? Therefore, p of x is reducible over f. So that's the proof. So in other words, if polynomial in question is just of degree 2 or 3, then the reducibility can be determined by well, whether p of x has a root in f or none. For example, let's look at the polynomial x cubed plus 3x plus 1, and let us show that this polynomial is irreducible over q. Now, to prove that this is irreducible over q, we only need to prove that, because this is of degree 3, that this doesn't have a root in q. But recall from the rational root theorem, do you remember this theorem from the previous lecture? You have to do this. So the only possible roots for this polynomial are the fractions of the form a over b, no? Where a divides 1 and b divides 1. What is this 1? This 1 is the 1 here, the constant term 1, and this 1 here is the leading coefficient 1, right? So as you can see, there are only two possibilities for this fraction, 1 or minus 1. But as you can see, by directly substituting, if you substitute x equal to 1, if you evaluate the polynomial x to x equals 1, you get this. Is this 0? No, this is 5, not 0. X is negative 1. You see that this is negative 1 cubed plus 3 times negative 1 plus 1. You see that this is negative 1 minus 3, negative 4 plus 1 is negative 3. It's also not 0. So because these are the only possible rational roots, and these are not roots, therefore x cubed plus 3x plus 1 has no root in Q. Therefore, because this is of degree 3 by the previous theorem, therefore x cubed plus 3x plus 1 is irreducible over Q. Okay? Let's now consider this quadratic polynomial x squared plus x plus 1. Okay? Over the field z sub 2, it is irreducible, while over the field z sub 3, it is what? Reducible. So let's see why. Okay? So let's name the polynomial as f of x if you wish. Okay? Okay. So over z sub 2, you see that there are only two elements in z sub 2. So we only need to check if one of 0 or 1 is a root. So if you evaluate f at 0, you see that this is 1 and not 0. If you evaluate f at 1, you see that 1 squared plus 1, when you do it over c sub 2, this is just 1, and again not 0. Therefore, f has no root over z sub 2 or in z sub 2. Okay, in z sub 2. Therefore, f is irreducible because it is of degree 2. Okay, but notice that over z sub 3, we have a different situation over here, right? Let's see why. If we evaluate, of course, f of 0, we get 0 squared plus 0 plus 1 is still 1. F of 1, 1 squared plus 1 plus 1. This time it's now 0. Okay? Ooh. So that means to say what? This means to say that x minus 1 is a factor of x squared plus x plus 1 over z sub 3. In fact, when you try to do long division, or you can just use synthetic division in this case, yeah, over z sub 3 tayo. So you see, sorry, over z sub 3 pala, so this is 2, 2 times 1 is 2, 1 plus 2 is 0. So you see that the other factor is x plus 2. Well, we don't need to do this anymore because we have already learned that once a root has been found in f, then already the polynomial is reducible as long as the degree is 2 or 3. Okay? Alright, next. This is a polynomial of degree 4. Okay? So, what are we going to do? So, as you can see here, because the polynomial has degree 4, it's more than 3, then the previous theorem is not applicable. So generally, determining whether this is irreducible or not is a, well, a hard task, right? But notice that I could write, well, let's check first, by the way, does this have a root in Q? Well, if you list down the possible rational roots, what are the possible rational roots of this polynomial? See that it's only 1 or minus 1. If we call this as f of x, you may evaluate f of 1, you get 1 plus 1 plus 1 is 3, and f of negative 1 is 1 plus 1 plus 1 is also 3. Therefore, x to the 4th plus x squared plus 1 has no rational root. Question is it irreducible? Well, the previous theorem is no longer applicable. You know, it is if the degree of the polynomial is more than 3, it is possible that a polynomial has no rational root, but still it is reducible. How can that be possible? In fact, this polynomial in this example is a reducible one. Let's look at this trick. Notice that I could write this as follows. I could write this as x to the 4th plus 2x squared. If I want to make this a perfect square, I have to make 2 squared, but I have to subtract an x squared, right? So now, you know that this is x squared plus 1 squared minus x squared. Because this is a difference of two squares, I know that this is x squared plus 1 plus x times x squared plus 1 minus x. Or you may rearrange if you want, like so. As you can see, I was able to still factor x to the 4th plus x squared plus 1 in a non-trivial way. even though that it doesn't have a root in Q. So the existence or non-existence of roots for a polynomial does not say anything about its reducibility, especially when the degree of the polynomial is more than 3. So you see, that result can be applied to polynomials over a field. Now, what if we wanted to ask the reducibility or irreducibility of polynomials over the integers? The set of integers is not a field, right? Okay, so that's what we are going to talk about in this slide. So let p of x be an integer polynomial. When a polynomial is an integer polynomial, we know that the coefficients are all integers. Therefore, we can take the coefficients as integers and then take their greatest common divisor, or the largest common factor, right? The largest common factor or the greatest common factor of all the coefficients of p of x is denoted by the symbol c of p of x, and it is called as the content of the polynomial. If the GCD, or if these coefficients are relatively prime, or the GCD or GCF is 1, then the polynomial is said to be a primitive polynomial. As an example, when you look at the coefficients of the polynomial 6x squared plus 4x squared, 6x cubed plus 4x squared minus 8x plus 18, you see that the GCD of 6, 4, 8, and 18 is 2. Therefore, the content of this polynomial is 2. On the other hand, this polynomial has 1, 3, 2, 4 as coefficients. These integers are relatively prime because their GCD is 1. Therefore, we can consider this as a primitive polynomial. In order to state the next result, we have to do the following notation. If you have a polynomial, an integer polynomial, to be more specific, and p is prime, by this symbol, we put the polynomial in a pair of brackets, square brackets, and then put a subscript p, like so. It denotes the polynomial obtained from f of x by reducing the coefficients modulo p. Coefficients ito. Lahat ng mga coefficients modulo p. How do we reduce? We divide by p, take the remainder. As an example, if I reduce 3x to the fourth minus x cubed plus 2x squared plus 11x plus 7 modulo 2, what does it do? Kapag odd, magiging 1. Kapag even, magiging 0. So, yung 3 na ito, mako-convert sa 1. Yung negative 1 na ito, mako-convert sa 1. Yung 2 na ito, mako-convert sa 0. Yung 11 magiging 1. Yung 7 magiging 1. Therefore, the resulting reduction is x to the fourth plus x cubed plus x plus 1. Notice that in this case, this polynomial is no longer an integer polynomial. It's now a polynomial in Z2 square bracket x. If we try to reduce the same polynomial, modulo 3 instead, what do you see? What do you notice? This becomes 0 modulo 3. Negative 1 is 2 modulo... No. No. Ulit. 3 is 0 modulo 3. How about negative 1 modulo 3? Negative 1 plus 3 is, well, 2. So it's 2 modulo 3. 2 modulo 3 is 2. 11 modulo 3. If you divide it by 2, take the remainder. What's that? 11 modulo 3 is also 2. 7 modulo 3 is 1. Therefore, the resulting polynomial is this. And this polynomial is now in Z3 square bracket x. Notice that sometimes when we reduce polynomials, the degree can be lower because the leading coefficient can sometimes turn to 0. Now, it is just now an exercise to verify that this reduction modulo p gives us a ring homomorphism from the ring of polynomials over Z the ring of polynomials over ZP. Okay? So meaning to say, this reduction of polynomials preserves addition and polynomial multiplication. So this is the theorem. Well, it's called as the Gauss lemma because it is being used um, well in a number of results. In fact, we will be using this lemma or theorem um, in the next slides. So according to Gauss, the product of two primitive polynomials, when we say the contents of polynomial this one, is also primitive. So for the proof, assume that u of x, v of x are integer polynomials which are primitive. We argue indirectly and we suppose that their product is not primitive. If the product is not primitive, it means to say that the content is more than one or it's not one, right? So if the content is greater than 1, we know that from number theory that it is now divisible by some prime number p. For example, 4 is greater than 1 is divisible by 2. Or in fact, any integer greater than 1 is now divisible by some prime number p. So let's say p is a prime that divides the content. It follows that okay, the content of q of x, no. When you try to reduce u of x modulo p times the reduced form of v of x modulo p, because reduction modulo p is a ring homomorphism, the reduced form of the product is the product of the reduced form, right? And because u of x times v of x has a content divisible by p, meaning to say each coefficient is divisible by p, if we reduce that modulo p, then that polynomial is 0 as a polynomial in ZP square bracket x. And since ZP square bracket x is an integral domain because ZP is a field, it, it follows that whenever by the zero product property that one of these polynomials must be 0. This would mean that one of u of x or v of x has a content which is divisible by p, which contradicts the fact that u of x and v of x are primitive. Therefore, the product q of x times v of x must be primitive. As for one of our main theorems, let's say p of x is an integer polynomial. If p of x is reducible over q, then it can be shown that p of x will be reducible over z. Meaning to say, if you can factor p of x, let's say, first of all, given that the coefficients of p of x are all integers, if you can factor that into non-trivial way into polynomials with rational coefficients, then according to the theorem, it can be factored in a non-trivial way into polynomials with integer coefficients as well. So to prove, assume that p of x, an integer polynomial, is reducible over q or factorable over q. So because q is a field, we can write it down in the form u of x, v of x, where these are polynomials of lesser degree but non-constant. Assume without loss of generality that p of x, or this product, is primitive, because if p of x is not primitive, then I can just divide both sides of this equation by the content. If I divide both sides of this equation by the content, which is the GCD of the coefficients, GCF of the coefficients, then the common factor for each of the coefficients will be just 1. So, magiging primitive na siya. That's why stated here. If not, divide both sides by the content. So, here, our assumption is that p of x is primitive. This time, let A and B denote the LCD. So, you can see that p of x, no? And by the way, u of x and v of x are rational polynomials. It's possible that the coefficients are rational numbers with numerators and denominators, right? You look at the denominators and take the least common multiple of the denominators. Okay? Let the LCD of the denominators of u of x be a, and the LCD of the denominator of v of x be b. Now, as an example, kunwari, ang u of x natin ay 1/3 x squared plus 2, well, let's say uh, 1/4 x minus 2/6, right? So what's the value of a here? We look at 3, 4, and 6. Take the LCD. LCD is 12. So therefore a is 12. Why would I want that? The next step that I'm going to do is I'm going to multiply this 12 to u of x. Because if I multiply each term by 12, I now just get 4x squared plus 3x minus 4. You can see it magically turns the polynomial into an integer polynomial. That's the idea. So that if you multiply the LCDA of the u of x, it becomes an integer polynomial. And if you multiply b by v of x, you get another integer polynomial. Now you get now a new integer polynomial, right? So they now have their contents of their own. So let's call by alpha the content of the resulting integer polynomial when you multiply a by u of x, and beta with the content of the resulting polynomial when you multiply b by v of x. And as you can see, a times u of x is equal to alpha times u1 of x. Now, the idea is that when you look at this polynomial, so the content is alpha. If I factor out alpha from this polynomial here, what remains inside is a primitive polynomial. For example, I get 2x squared plus 4x plus 6. The content is 2. If I factor 2, I now get a primitive polynomial. Okay? Right? Okay. So therefore, if we factor the content of a times u of x alpha, we get a primitive one. u1 of x is a primitive polynomial. Similar to that, if the content of this is beta, if I factor it out, I get something here that is primitive. We follow that. Now, by Gauss's lemma, these are primitive polynomials. It follows that this product is also primitive. Since by assumption p of x is primitive, the content of uh, ab times p of x should be ab because p of x is primitive in the first place, right? Right. Now, what is p of x then? Well, when you look at these equations, this equation and this equation, you multiply the left-hand side, you multiply the right-hand side, you get that ab times p of x equals alpha beta times u1 times p1, like so. Now, because again, this one is primitive, alpha times beta is a constant, then the content of this polynomial is just alpha beta. Hence, the equality of this implies that because these two are equal and non-zero, you can divide that. Therefore, I was able to write p of x as a product of u1 of x times v1 of x, where u1 of x and v1 of x are primitive integer polynomials. Furthermore, the degrees of these polynomials did not change from u of x and v of x, and therefore p of x is reducible over z. Okay? So, we started by assuming that p of x is reducible over q. We have concluded that it's also reducible over z. The proof is quite confusing at first, but it will be clear when we give an illustration. how the proof worked. Okay? So for example, you consider the integer polynomial 6x squared plus 7x minus 20. Now I used, well, a skilled factorization. I was able to come up with this factorization. I just need you to check that this is correct using the FOIL. Now, using the FOIL, you can verify that this is indeed, these two are indeed equal. So in other words, this polynomial, I was able to factor it over Q, right? Can I factor it over Z, or can I choose the coefficients? Well, can I do another way to factor, but now only integers are allowed as coefficients? Well, according to the previous theorem, yes. If you can factor it over the rational, then you can also factor it over the integers. That's the idea of the previous theorem. So here, what we do is, what? We take the LCDs. So we only look at the denominator. So 3 has denominator 1, this has denominator 2, the GCD is 2, LCD is 2, so that's A. For this, the LCD is 3, so that's B. What we now do is we multiply the LCDs to the given polynomial. So if I multiply this by 2, I get 6x plus 15. If I multiply this by 3, I get 6x minus 8. Now, the resulting polynomial are now integer polynomials. They now have their respective contents. The content of this is now 3 because the GCD of 6 and 15 is 3. That's the alpha. The content of 6 and 8 is 6x minus 8 is 2. That's now the beta. What we do is we factor the content over here. So we factor out 3. What's left inside is 2x plus 5. That's u1. If we factor the content 2 from here, we get 3x minus 4 as the other factor. Do you remember this equation? Yeah. So this equation implies, or in this case, by the way, it converts or it translates to this. Well, because 2 times 3 is equal to 3 times 2, you can divide by both sides, and this gives us the following factorization. That's why 6, if you can factor it over the rational, the proof is telling you how to factor it, or how to select the factor so that the coefficients are all integers. We get that. Now, the real use of the previous theorem is not for reducibility. Actually, the real use is when you take the contrapositive. It states that if you can somehow find a way to prove that f of x is irreducible over z, then you can already conclude that it is irreducible over q. And why is this significant? Well, first of all, z is not a field, but q is a field. Do you see that? Okay, that's why this is significant. If you were able to prove that a polynomial is irreducible over z, automatic siya irreducible din over q. So our next question will be, how do we know irreducibility over z then? Now, it turned out that there are well-known tests. And in this lesson, we will be talking about two well-known tests for irreducibility over z, whenever the coefficients are integers. These are the mod p test and the Eisenstein irreducibility criterion. So Eisenstein, I think Ferdinand ang pangalan na ito. No? He was a student of Gauss. So without further ado, let's introduce the mod p test. How do we perform the mod p test? So here you select a prime number p. It is upon your choice. F of x is a non-constant integer polynomial. So what we do is we reduce the polynomial modulo p of your choice. This one is your choice. If the resulting polynomial is irreducible over zp, if you were able to establish the irreducibility over zp, but this is quite easy, especially when the degree is less than or equal to 3. Why? Because zp is a field, you only have to know whether this has a root over z sub p by simply evaluating f of x mod p to each of the elements of zp and know kung siya ay mag-zero or hindi. Kapag nag-zero, yung degree na ito ay less than or equal to 3, it's lang. Pero kapag hindi pala nag-zero, by the way, kung hindi pala nag-zero, sabihin nun, irreducible. Right? Kung ito daw ay naging irreducible, at ang degree ay hindi naman lumiit upon reduction. No, upon reduction, hindi lumiit yung degree. Katulad ng example ko kanina, lumiit yung degree, right? Then we can conclude right away that f of x is irreducible over q. Okay? So why is the mod p test true? So let's see the proof. Well, suppose, again, for the sake of contradiction, suppose that f of x is reducible over q. Again, you can write f of x as a product of two non-constant integer polynomials. Now, why can we select integer coefficients? Because according to the previous theorem, by the way, the reducibility over q means that I can write f of x as a product of two rational polynomials, non-constant rational polynomials. The previous theorem guarantees that if you can write it down as a product of two rational polynomials, then you can also write it down as a product of two integer polynomials. Each has degree less than that of f of x. So, reducing modulo p, so because the reduction modulo p is a homomorphism, this will happen. And that when you look at the degree of the reduced form of u of x modulo p, it cannot exceed the degree of u of x because this is where it came from after the reduction. Now, because this has degree less than f of x, and the degree of f of x equals the degree of f of x mod p by assumption, and similarly, by the way, ganun din ang mangyayari for v because this is just the other factor. Hence, I was able to write it down or reducible over z sub p, which contradicts our assumption that f of x is irreducible over z sub p. Therefore, f of x must be irreducible over q. Okay, let's look at this example. Is this polynomial reducible over q? Can I factor it using non-trivial? Can I factor it in a non-trivial way using rational polynomials? That's the question. As you can see, because this has degree 3 only, degree 3, right? You can only check the possible rational zeros of this polynomial. But see, in this case, the rational root theorem is kind of hard to apply because the possible rational roots can be plus or minus 9, plus or minus 3, plus or minus 1, plus or minus 1 over 31, plus or minus 3 over 31, plus or minus 9 over 31. And then it will take us a lot of time to check each one of those kung magiging zero yun or hindi. Yeah? It's kind of hard to determine. Tapos wala naman palang mag-work doon. So, irreducible. No? But we can see, ito yung advantage ng reduction modulo P. So, let's take the smallest prime is 2. No, wala nang masama at piliin yun 2. If we reduce fx mod 2, what do you think is the answer? Mod 2, this is just x cubed. 31 mod 2 is 1. Minus 18 mod 2 is 0. So, mawala ito. Mod 2, 11 is 1. Mod 2, 9 is 1. So, I now have the polynomial x cubed plus x plus 1. This time, this is in V2 square bracket. Now, let's call this as f of x if you wish. Okay? No, I cannot call it f of x. Let's say p of x naman. Now, let's try one by one. P of 0, hindi siya 0. P of 1, dalawa lang naman ang elements ng ng v sub 2. So 1 again. So none of this is 0. So in other words, p of x has no root in z sub 2. Therefore, p of x is irreducible over z sub 2. Nung ni-reduce ko ba, lumiit yung degree? That's one thing you need to check. Hindi naman, degree 3 pa rin. Kumbaga, kailangan yung leading term ay hindi nagsi-zero. That's one of the assumptions. So p of x is irreducible over c sub 2. By the mod 2 test, no? Mod p test, therefore f of x is irreducible over q. That's it. Oh, let's take another example. Show that x to the fourth plus x plus 1 is irreducible over q. So this time, even when we reduce it modulo 2, for example, no, it's not um, easy to determine whether this one is reducible or not. Kasi the existence of the root, because this has degree more than 3, the existence of a root doesn't mean that, the non-existence of a root doesn't imply irreducibility. Sometimes, pag degree 4 and up, kahit na walang root, sometimes reducible pa rin. No? And let's try our luck. So let's consider reducing it modulo 2 once more. So if we reduce this modulo 4, modulo 2, you see that modulo 2, it's still the same. Yeah? But this time, kino-consider na natin as a polynomial in z2 square bracket x. Kanina over q pa siya. No? This time, it's in z2 square bracket x. Okay. So, paano na to? So, well, let's check if there are roots. Kasi, you know what? Ha? Kung mayroong root, ibig sabihin, makakuha ka ng other factor. Pero syempre, i-expect natin wala makukuhang root. Kasi nga, irreducible, no? So natin, kung, kung if you take p of 0, you get 1. P of 1 modulo 2 is 1 plus 1 plus 1. Modulo 2 is 1. So none of this is 0. So we can only conclude one thing. We cannot conclude about its reducibility or irreducibility over z2. We can only prove that, or we can only say that x to the 4 plus x plus 1 has no linear factor over p sub 2. That's the only thing that we can conclude right now. So meaning to say, if x to the 4th plus x plus 1 is reducible, if, I'm not saying it's reducible, if it was reducible, then the only factors, then it must have quadratic factors, two quadratic factors. But what are the quadratic polynomials? What are the quadratic polynomials in z2 square bracket x? Dahil z2 tayo, konti lang yan. Right? Hindi masyadong marami. In fact, we can enumerate. What are those? Well, x squared. Okay? So, pwedeng x squared plus 1. So, pwede namang x squared plus x. No? So, pwede rin namang x squared plus x plus 1. Meron pa ba over z sub 2? See that there are only 4. But I can already tell na some of these are not factors of this. Why? For example, this one, x squared, is not a factor. Because x squared is x times x. It has linear factor. If this was a factor of x to the 4 plus x plus 1, then this will have a factor of x as well. In other words, this will have a linear factor contradicting this. Therefore, this is not a quadratic factor because this has a linear factor. How about x squared plus 1? X squared plus 1 also has a linear factor because we are working over z sub 2. It's x plus 1 quantity squared. So again, using the same logic, this cannot be a factor of x to the 4th plus x plus 1. Also, this one cannot be a factor because that's x times x plus 1. How about this? How about that? Can we factor it? Does this have a quadratic factor? Well, if this was a factor of this one, then dapat pag dinivide ko ito by that, I get a remainder of 0. But if we perform long division, let's try. If we perform long division, or if we apply the division algorithm, okay, so x to the 4th divided by x squared, we get x squared, tapos x squared, x to the 4th plus x cubed plus x, you subtract, you get, or we're working modulo 2 ha, you subtract, wala ito, minus x cubed, but that's just x cubed, x minus x is 0, plus 1, so I get x cubed plus 1. So degree of this is 3, not yet done, so divide again, x cubed plus x squared plus x. Tama ba ako? Yeah. Subtract once more, mawala ito. Minus x squared is just x squared. Minus x is just x. 1. Not yet done. If we divide, oh, what happened here? Ano mangyayari? Divide ba? Wait, parang may mali. Let's repeat the long division, ha? Okay, there you go. I did the long division in the background para hindi masayang yung time natin. Okay, so there, I did the division. I found that it has a remainder of 1, not 0. Meaning to say, this can't be a factor, right? Because it has a remainder. So therefore what? Therefore, none of this is a factor. If the only way to be reducible is to have two quadratic factors, then therefore that's how you prove that x to the 4th plus x plus 1 is irreducible. Ano yung sinasabi ko? Sometimes, proving irreducibility, especially when the degree is more than 3, can be very hard because sometimes you have to uh, resort on, tawag dito ay exhaustion. No? Kasi lahat ng mga possible cases ay kino-consider na. Okay. Let's look at another example. So this is a polynomial over Q. Because the coefficients are rational. Bibigyan ko kayo ng hint. No? Example, you can consider the LCD of the um, denominator. Okay? LCD is 6. 6 ba? 6, yes. If you multiply p of x by 6, you get what? You get 3x to the 4th. Okay, tama ba ako? 3x to the 4th plus 4x cubed plus what? 8x squared plus 15x plus 21. Is that correct? So this time, this is now in z squared bracket x. Now take note that p of x will be irreducible over q if this one is irreducible over q because it is just a constant factor. We ignore constant factors over q because they are just units, right? So the irreducibility of this will imply the irreducibility of this. So proving that this is irreducible over q is the same as proving that this is irreducible over z. What can we do? We try to reduce modulo 2. What's the result? X to the 4th. This one will go to 0. This one will go to 0. 1 will go to 1, that 1 will go to 1. Oh ho! Naalala niyo yung polynomial natin na nakaraan. We know that this is irreducible. Hindi naman lumiit yung degree. So, by the mod 2 test, this has to be irreducible over Q. And the irreducibility of this over Q will imply the irreducibility of this over Q. So this is a trick question actually. Now one more test, or one last test, is the so-called Eisenstein criterion for irreducibility. Again, banggit ko, no, si Eisenstein ay student ni Gauss. Maybe when he was studying. So this is kind of hard to remember, but you have to remember. Okay? So here you're given a polynomial with integer coefficients. Walang restriction sa degree or anything. No? So what you're going to do is you're going to look at the coefficients from the degree n minus 1 pababa. Okay? Maghahanap ka ngayon ng prime number na dinidivide lahat ito mula dito pababa. P must be the divisor of a sub I from 0 to n minus 1. Meaning to say, a common prime factor to each one of these. So that, hindi lang siya basta common prime factor ha, may requirement. Dapat yung prime na yun, hindi dinidivide yung leading coefficient. So in other words, magandang gamitin itong Eisenstein kapag yung leading coefficient ay 1. Kasi automatic, satisfied na yun. At the same time, ito yung last criteria, last assumption ni Eisenstein. Kailangan yung square nung prime na yon, sabihin, walang dalawang p ang magkakasya doon sa a0. Kailangan pag in-square mo yung prime, hindi niya pa rin kayang i-divide ito. In other words, pipiliin mo yung p, maliit pero not small enough kasi baka yung square niya ay ma-divide sa a0. No? Kung may makikita ka raw na ganyang p, we can conclude kasi f of x ay irreducible. As you can tell, no, we are always in the direction of proving that a polynomial is irreducible. In fact, in our subject, irreducible polynomials will matter the most, right? As you can see in the next few lessons, kapag meron kang irreducible polynomial, we can construct a field out of that, where the given polynomial has a root. Basta, we will be talking about that in the future lesson. The existence ng roots ng polynomials will, halimbawa yung polynomial, walang solution sa field na ito. No? Yung, well, yung irreducibility ng polynomial can help us find a field, a larger field, where a root can be found. Parang yung x squared plus 1, wala siyang solution sa R, pero sa C, meron siyang solution. Can we always do that? Kapag ang polynomial walang solution in a given field, can we find a field larger than that where a root can be found? Turns out that the answer is yes. May plane na ginagampanan ang mga irreducible polynomials. That's why our direction is always to proving irreducibility. Okay, balikan natin ang Eisenstein. Kailangan makahanap ka ng p na dinidivide yung mga coefficients mula sa una hanggang sa n minus 1. Na hindi dinidivide yung una, pero ang square, hindi rin dinidivide yung nasa dulo. Okay, so let's prove the Eisenstein criterion. So the proof again is by contradiction. Kunwari nare-reduce yung f of x. Again, we can factor f of x in a non-trivial way, like so. This time, bibigyan natin ng katauhan yung u at saka yung v. Kunwari, ito si u, degree r siya, si v ay degree f. Pero dahil ang product nila ay f, ang degree ni f ay n, kailangan yung r plus s ay equal sa n. By hypothesis, dinidivide ni p lahat ito. In particular, dinidivide niya sa a0. But how do we get this a0 kung product siya ng u at v? Diba nakukuha to by multiplying the constant terms of u and v. So, meaning to say a0 is b0 times c0. So if p divides this product, or p divides this product, that's a fact. Now, and because p squared does not divide a0 by hypothesis, dinidivide niya a0 pero square hindi, meaning to say, what? Isa lang daw dapat dito ang pwedeng i-divide, isa lang daw dapat dito ang pwedeng i-divide ng p. Bakit? Logic yan. No, why? Kasi kung dinidivide kasi ni p, parehas ito, so each one of this will have a factor of p. Ang mangyayari, madi-divide na to by p squared. Eh hindi nga. Kaya dapat dinidivide ni p yung isa lang dito at yung isa dapat hindi. Do you understand the logic? O kunwari na lang. Si b0 ang dinidivide ni p pero si c0 ang hindi. Okay. Also, it's given that p does not divide the leading coefficient. The leading coefficient, kung alam niyo yung mag-multiply ng dalawang polynomials, no? Makukuha niyo leading coefficient by multiplying the leading coefficients of the factors. So, ang an ay br times cs, correct? Kung hindi dinidivide ni p ang br at cs, dapat hindi niya dinidivide parehas. In particular, that hindi niya dinidivide ang br. Ang gagawin dito, ganito. We will consider the set of all n, no? So that p does not divide b sub n. We'll consider all the index n, no? Where p does not divide bn. Well, first of all, this set of natural numbers, this is a set of natural numbers, by the way. Or maybe including 0. Basta, si R ay naririto. Meaning to say, this set is not empty kasi nga dahil dito, si R ay naririto sa set na ito. Ito ay set of non-negative integers, for example. At siya ay non-empty. Anong meron yan? Sabi sa number theory, yung tinatawag na well-ordering principle, this set must have a smallest element. Let that smallest element be denoted by P. I mean to say, si P yung pinakamaliit na subscript ng B for which P does not divide BT. That means that for indices smaller than T, dapat dinidivide ni P yung mga yon. Kasi ito na yung pinaka-kauna-unahang i-divide ng P. So then, for indices or for the B sub i's where the index come before T, lahat yung dinidivide pa ni P. So, the hypothesis of the theorem implies that P divides 80. Why is that true? Kasi, ganito, si BT, may katapat yan na 80, right? Right. Yung T na yan, it cannot be N. Otherwise, lahat i-divide niya, na be something smaller than N. So, dapat yung 80, sabi kasi na ito sorry. Saan ba ako naligo? Ayun. Ito siya. Dinidivide niya kasi yan, kaya dapat i-divide ni P yung 80 in particular. Now, yung definition natin ng polynomial multiplication, yung pang T na coefficient ng f of x, can be calculated using this weird product, diba? Yung rule, kailangan pag ina-add mo yung mga subscripts, kailangan T. Diba? Ito lahat ng mga terms na yun. But as you can see, mula dito, look at this. P divides BI, I for less than T. So then, dinidivide ni P si BT minus 1, si BT minus 2 hanggang B0. Therefore, i-divide ni P lahat ng terms na ito. If P divides all of these terms, and P divides 80, it must divide this one. Right? So, P now divides BT times C0, Mm, this is a contradiction. Why? Because P neither divides BT, no? P does not divide BT, and P does not divide 0. So, ito, yun. Nakalagay sa taas. Hindi divide ni P si C0. Hindi rin dinidivide ni P si BT. Sorry, ito pala. Mali ako na highlight. But ang nangyari in the end, P divides this product. So that's impossible. So therefore, f of x is irreducible over Q. As an example, how do you check the irreducibility of this? Ang gagawin natin, maghahanap tayo ng prime factor 18, 48, at saka 24. Anong palagay niyong P? Anong palagay niyong P? Can I use 2? I cannot use 2 because 2 squared, can P be 2? No, kasi ang P squared is 4, it will divide 24. It's not a good choice for P. Remember, again, Eisenstein, P divide I from 0 to n minus 1. P must not divide an, and P squared must not divide a0. Kailangan yung constant term hindi na-divide sa P squared. So what P is possible? Right, 3. If you select P equal to 3, as you can see, 3 divides 18, 3 divides 48, and 3 divides negative 24. And then 3 does not divide 1. Kasi yung leading coefficient mo ay 1. Sorry, not pala to. And 3 squared, which is 9, does not divide the leading coefficient negative 24 as well. So therefore, by Eisenstein criterion, sabihin nyo na lang na in a narrative form, by Eisenstein, this cannot be reducible, therefore it is irreducible over 2. Last example, let n be greater than 1 and p be a prime number. Prove that the nth root of p is always irrational. What is this? How do you proceed? Well, um, the hint is to consider. It's very wise to consider the polynomial x to the n minus. Why do I consider this? Because if you equate this to 0 and you try to solve, lagyan natin ng quotation, solve for x, you'll find that x is the nth root of p, right? Now, you see that this is an integer polynomial. Leading coefficient is 1. The constant term is negative p. And the coefficients between the first and the last terms are all zeros. So you can just consider the prime p. Note that p divides every term, no? P divides every term, sorry, every coefficient except the last term, the leading coefficient, the leading one. Else, huh? P does not divide the leading coefficient, which is 1, and p squared does not divide p because p is prime. Minus p for that matter. Minus p for that. Yeah? So by Eisenstein, parang Einstein yan, hindi Einstein talaga. It's Einstein. Okay? Eisenstein. Magagalit sa inyong mga German kapag binasa niyo ng Einstein. Okay, Eisenstein. Or maybe in English, I don't know. But nasanay ako kasi mga teachers ko, ganun ang turo. No? Eisenstein. Einstein. Einstein. Ganun yun. Kunwari galit. So, ano sabi ni Eisenstein? Eisenstein tells us that x to the n minus p is irreducible over q. And magpo-follow na xn minus p has no linear factor over q. Therefore, xn minus p has no root by the factor theorem. Therefore, that means kung meron mang itong root, actually x nth root of p is a root, no? It cannot be rational. Therefore, the nth root of p, whenever p is prime and is greater than 1, is always an irrational number. Right? So, meron akong exercise para sa inyo. Actually, nandito, ito yung nasa lecture notes niya. I just want you to read or write if you may wish. Later on, we will call this as the p-th cyclotomic polynomial. So, ang p-th cyclotomic polynomial daw ay irreducible over q. Anyway, so we will continue this lesson. In the next lesson, pag-aaralan natin anong magagawa natin sa mga, kung hindi ma-factor ang mga irreducible, can we make something bright or can we make it useful? Meron ba tayong mapapalang iba kung hindi na-factor ang isang polynomial? So we will see. Okay? See you next time.